Hello, so today I'd like to talk about David Cohen's An Introduction to Hilbert Space and Quantum Logic. This is a very interesting book because it bridges basically functional analysis, you might call it functional analysis, and quantum mechanics. And it has this bridge here for you in a very light volume, right? So these are still solutions to problems, so about 104 pages. 104 pages before you get to maybe not solutions, but hints and stuff like that for the problems. So it's a very short book, and it bridges mathematics and quantum mechanics in a very strange way. This was a book that was written basically for classes taught at Smith College. Now, I picked up this book, I think, probably before I took that functional analysis class in college, which was the last class I took in college. And I think I've read it 3 times now. I think I read it 2 times before I decided to do this, and twice or once after that, so that would be 3. So I think I read it earlier, right? I had some notes in it, which means I probably read it sometime after 2012 or so. And I have a very important note here. And then I just read it again in my current note-taking format. So I think we'll have a pretty good time talking about this. But there are 2 things in this book that I think are really important. Now, the provenance of this book, how I actually ran into it, I don't think it's in print anymore, but find out. I'll put an Amazon link to the best link I can find, which is probably going to be used in the description. But I found this book because when I went to school, I was at a campus that basically had 3 different colleges on it. A community college, a 4-year college, and a university. And each one used the same bookstore. And one of the best things about that is that they had an entire row of Springer books. They always had an entire row of these Springer books just sitting there for you to buy. It was awesome, right? You could just wander in and look at all of these cool books. In this case, An Introduction to Hilbert Space and Quantum Logic. Let me see. Do I see my differential forms book just sitting around for me to grab? And I do not. So that's the only one that I'm absolutely sure that I got there. And I do not see it. So there are other Springer books that I have, but there are only a couple that I'm sure that I picked up at that place because I remember something particular about it. So that was just awesome. That was just awesome. I was so sad when I went to a real college and I found out that the college bookstore sucked. It was basically a place for you to pick up the books for your classes and some crap that you never really want to read anyway. So this book, like I said, has a little bit of math in it and a little bit of physics, and it was taught by a mathematician, and there's a bridge in there. So I'm going to talk about this. The interesting thing is basically in his class, this is a short book, but in his class, for a semester-long class, he only used parts of it for any one class, and some of them weren't used in any class. So chapter 1 was never used, and experiments, measure, and integration. 7 and 8 were never used. That's spectrality and the Hilbert space model for quantum mechanics, at least according to his preface here, and how he used it in particular classes. He used it differently in different classes. Did he have average students? Did he have really good students? But he didn't use some of these things, including chapter 8, which is the EPR paradox, which is one of our favorite things, right? That's everybody's favorite thing. So I'd like to talk about what I liked about this book, but I'll do it in the standard way, which is to go through the table of contents. So we start off with a chapter on experiments, measurement, and integration, just to sort of talk about some issues. You know, how experiments sort of work with weight functions and expected values and things like that. These are fairly standard. It's not too interesting, except that it's done in a very mathematical way. So you get a very theoretical basis for all of these things. But you can see, signed measures, complex measures, measurable functions, all very normal. Almost everywhere equality. That's something he does use in the book. And it's a very strange idea. Well, it's not too strange an idea, but it's saying that two functions are equal, or almost everywhere equal, if the places where they are not equal is or are, well, make up a region of zero measure. So you think about that as like if you had a real number, if you had a function on, x on a real number line on a position or something like that. If the function was, if two functions of x are the same on all real numbers and different on all rational numbers are infinitely smaller than real numbers. So if you take an integral over those two functions, you should end up with the same integral, right? Because the little rectangles, if you're thinking about the Riemannian integration, for those rational numbers are infinitely small, and they just don't account for anything in the end, right? You have basically a measure zero area that can be represented by a finite sum, right? That just does not do anything for that integral. Such functions couldn't be integrated technically with a Riemannian integral. And that's why he talks about Lebesgue measures and Lebesgue integration, which are just other ways to integrate. So there's some functions that are technically not integrable, and ways to sneak around that already, right? So if you have a step function, technically it's not integrable, but you can break it up into two integrable regions and add them up, and everything's okay. But if you're a mathematician, everything has to be logically sound. Everything has to be based in pure, well understood background. And so, you get this problem where some functions, like the step function that I just said, don't technically have a Riemannian integral, the integral that you learned in Calculus 1. So Lebesgue basically found another way to define the integral, and he talks about this a little bit. If you take an advanced calculus course, they'll talk a lot more about it. A real analysis course, they'll talk a lot more about it. So when I first read this book, and I'd just come out of a functional analysis class, lots of these ideas were very, very clear for me because, I'd just done them all. I just spent a semester doing all those things, and they were all still in my head. The weird thing about this Lebesgue measure is that technically it's no longer an antiderivative, right? So the Riemannian integral is identified with the antiderivative. The Lebesgue integral is not, but they basically are anyway. So you don't have to worry too much about that unless you're proving things. If you're trying to prove things, then it's really, really important. So then we go into the basics of the Hilbert space, how to define the inner product and define a space on an inner product, and what sort of vectors make up your Hilbert space and so forth. An inner product is a little bit like a dot product. A dot product, I think, would satisfy the definition of the inner product, but it definitely would satisfy the definition of the inner product. The thing is that that's not necessarily what we want to do. In fact, if you come down here in these examples, this is what we do in quantum mechanics, right? Is you integrate you find the inner product of these two functions by integrating over psi1 times psi2 star, the complex conjugate of psi2, over some area d mu, or some area S, right? And at that point, after you've done the integral, you have, well, we'll call it a probability later on, but that integral gives you a measure on a measure of this overlap sort of thing. So that's why we care about all this stuff, is because we're building up basically to a Born rule or something like that. Next we'll get the logic of non-classical physics. So we're now going into quantum logic, which is a little bit different from quantum mechanics. It's a little looser actually than quantum mechanics. In this case, first you try to talk about manuals of experiments and weights, right? These manuals are like having a little book, and in that book it tells you all of the things that you can measure together, the possible experiments. So you can measure Sx with S, but not Sy and Sz together. So, this manual tells us stuff like that, and it tells us other important things about weights and uncertainty and so forth, dispersion. Here he talks a little in specific about electron spin. Then we have logics and state functions. So now that we have this logic, we want to use that to create a state function. And in this, get into an interesting discussion here, because he's going to start talking about partial orders. Let's see, this is just a tree for a lattice, which would become a partial order. So a partial order means that there are states that are part of parts of other states, but not parts of a third state, right? So the state that the first state is part of is a substate of. You can use some sort of reasoning with that, but if it's not a part of that other state, if you can't measure it in the other state, basically if the variables don't commute, right? You can't take two measurements in. You can't take measurements in different places. You can't take a Sz and an Sy, this X and Y components of the spin. You can't measure those simultaneously. So you couldn't, if you measure Sx in one experiment and Sy in another experiment, you can't sort of put Sx and Sy into the same state function. So if you have a state function that has Sx and a momentum, let's say Py, then an Sy measurement is not going to be part of that. It's not an independent measurement, and so you don't get sort of independent probabilities out of it. Whereas if you have the Sx measurement itself, that's a sub measurement, let's say, of that other one. It can be a component of that other vector. So you have a partial order. You can't say anything about, well, Sy has this probability, so Sx Py has some other probability, right? You can't talk about that. They're not in the same lattice, right? They're not on the same branch of a tree of different possible measurements. So you can't talk about their probabilities simultaneously. You have to choose which branch you talk about. Okay, that's just some basic logic from lattice theory. Somewhere I have a lattice theory book as well. That was really freaky when I tried to read that when I was a lot younger. So here we get into these logics, right? I wonder if I have anything written down about epistemic and ontological uncertainty. Here he's talking about pure states, so pure states become important for the logics. And I don't have anything written down, so let me just try to look at it. So we can look at the uncertainty, right? We can look at the variation in our measurements either as we can't make our measurements precise enough to measure something to, to a better degree, or we can say ontologically that the thing we're measuring can't be said to be more precise than that. And what we'd like to say usually, or classically, is that we have an epistemic uncertainty, that we have a measurement uncertainty. But instead, we usually have an ontological uncertainty in quantum mechanics. That's how things are usually interpreted. That is, because of the uncertainty principle, there's a minimum uncertainty we can find about what's going on, but that minimum uncertainty is real. It has something to do with the real world. It does not have to do with something just about our measurement system, but it has something to do with the underlying structure of the universe. So that's pretty important. We talk about subspaces on Hilbert spaces next. Oh, that's completely mathematical. I don't think we need that much more. We don't really need that, except that it's building up for the maps on Hilbert spaces, which builds up to state space and Gleason's theorem. So this is all very mathematical. This is all very important for the functional analysis, and it only ends up being important for quantum mechanics in that at some point this becomes important for something else we'll talk about in just a second. So now we'll talk about maps on Hilbert spaces, Hermitian operators and things like that. This is basically telling us what sort of things we have in our Hilbert space that makes sense as far as what we're doing. So we have Hermitian operators. Those are what we're going to call measurements. Then we go to projection operators here and the projection logic. The projection operators are going to be sort of the basic, or going to give us basis states, basically, out of states. It's going to tell us if we do this measurement, what is the probability of getting this particular state out of it. So that's going to be really important. Summation of operators and things like that. These are very important things. You have to build them up very slowly because you're doing mathematics and you want to justify your steps. But they aren't the things that we normally use in quantum mechanics themselves. Well, these are the things we're using. We're using quantum mechanics themselves, but this is just showing that they work. Then we get into the state space. State space is what we're usually working with in quantum mechanics. What state do we have before a measurement? Then we do a measurement, which is generally represented by an operator, and then we get a state out after we do the measurement. So that's what we're looking at. So this is an abstract space in the sense that what we're talking about are what are the possible states, what are the things on these maps that we can use to, what are the places on the maps, the things in the manual that make sense as far as the measurements that we make. And this talks about observables and the spectrum you get and things like that. Expected values, exposed faces, that's a little tricky. I didn't really get that even now. I don't know if I got that when I first read the book. I may have understood it, but I definitely don't really understand that too well now. It's a pretty abstract way of talking about what can and cannot be measured. And we have Gleason's theorem. This is pretty important. This is one of the things that you don't really get elsewhere. Gleason's theorem basically says every observable on a Hilbert space is associated with an operator, and every state is associated with a vector. Basically, it's saying your Hilbert space is a good match for quantum mechanics. So you can actually do your quantum mechanics with, and everything's fine. The weird thing, though, that I wanted to talk about is that being able to put these restrictions on quantum mechanics, the Hilbert space is a little more restrictive than is strictly necessary for a complete description for what we want to do, but it's never been shown that these restrictions are inconsistent with experiment. That is, the Hilbert space formulation, the formulation we're used to using for quantum mechanics, is more restrictive than is strictly necessary for the sorts of things we do with quantum mechanics. But whenever we try to find a difference between the things, in those cases, it's never really that much different. It never really shows up there is a difference. So we haven't found a difference between that. So I think that's something that's very interesting. Maybe you can find a place where there is a difference, where the Hilbert space formulation doesn't quite work, because technically it's not really necessary if you just look at the postulates of quantum mechanics. There's some extra structure in that Hilbert space that is not required for the basic postulates of quantum mechanics, at least according to Cohen in 1989. So whether or not that's still true, I'm not sure. But that was what I got out of it. Let's see, Chapter 7. Spectrality. This is basically, the finite dimensional spaces and infinite dimensional spaces. We can break these up, but basically what this is going to say is that each projection that you make is associated with a measure on that system. Basically, you make a projection, you're saying, can I measure something with that projection operator, or what is the probability, basically, in the end. And any operator can be represented as a linear combination of other operators. So that's basically what we do anyway, right? So again, this is a math book. It's about showing that the things work out, not necessarily that it really gets there. And then the last one, which again is not something he actually got to in the classes according to his preface, is basically history of quantum mechanics and the EPR experiment that is everybody's favorite, right? That basically shows that you have to use a quantum idea of probability rather than a classical idea of probability to make everything work out. So you have to have all of these different aspects of what's going on. In the end, you have to use you can't use your classical intuition that comes from, playing Keno at the casino. You have to have a better idea about what's going on. So this is a really interesting thing, but he didn't really get to it in his classes, though maybe he ended with it or something like that, something interesting, just to send everybody off with. So that's what we have in the book, right? The big thing being Gleason's theorem. I checked a bunch of books that I have, and I didn't really see it anywhere. So even though it's sort of fundamental to being able to use the Hilbert space, if you're in quantum mechanics class, they just sort of assume that you can use the Hilbert space. People have been using it. It hasn't broken, so it's okay, right? In functional analysis, it doesn't even show up, right? They don't care that you can use this for quantum mechanics. It's no big deal. So this Gleason's theorem is an interesting mathematical curiosity that shows that you can use those Hilbert spaces. Again, the most important thing from the book was that the Hilbert space is a little more restrictive than you technically need from the postulates of quantum mechanics. Let's go through a section here. because this is a math book, it has its own way of doing things, right? So this is fairly common in a lot of different kinds of math books, right? He talks a little bit about what he's doing, right? This is his Firefly experiment, which is sort of a classical analog to the EPR paradox. And now he's going to do some things. So he's defining first a quasi-manual, because in this case he's building up what a manual is. And then he does some and then he does more definitions. So he does a bunch of definitions. That's how more or less your mathematician starts out. Talks a little bit about them, why they're important, and then he goes and has some examples for you to do. So an example for a mathematician is a project for you, right? You are supposed to do the project. And when you do that, you're ready to go on to the next part. There's a definition. I'm not seeing theorems, more projects. So the projects are, again, things to make sure that the projects are there for you to make sure that you understand what's going on, right? Because this is how you do things. Is you learn by doing things, right? And in this case, I'm just seeing definitions and examples. I'm not seeing any theorems. Obviously, this is a Stern-Gerlach experiment, so he talks a little bit about this back here. And later on, he does more. So let's see here. Okay, here we have lemmas, right? So we go to part B, a definition, lemma, definition, lemma, lemma, definition, examples, lemma, definition, and so forth. And there's a theorem. So De Morgan's laws is a theorem. So he's basically building up logics in part B. So he wants to have De Morgan's laws as a theorem because De Morgan's laws are really important for a logic, right? And more theorems, another project, or the proof is left as a project. There are a lot of those in here. An example in a project, a lemma, a definition, and so on. So that's the way the book is set up, which is a fairly common way for mathematics books to be set up. So again, very nice little book, short book, kind of dense. It is worth going through if you're okay with mathematical reasoning. If you're not really okay with mathematical reasoning, it's going to be really, really hard going. It is terse. It's only 104 pages. In the end, there are problems. You should do the problems. In the back, there's this coaching manual, which takes up about half as much space as the actual book. And this is sort of hints about how to go about the different examples and projects. How do you actually, there are hints on how to prove some of the theorems. So he, like I said, he leaves some of the proofs to the reader. He has hints on how to prove them in the back. So that's also helpful if you're having trouble, if you're not used to that sort of thing. If you're not used to proofs at all, then this might be a really tough book. But, I mean, it is worth going through just to look at how you can mathematically justify the things in quantum mechanics. So this is a bridge basically from mathematics to theoretical physics. And then there's one more bridge from theoretical physics to experimental physics, from theory to the real world, which I shouldn't have put on this book because this is one step back from that. And if you have some idea about what quantum mechanics is, and you don't have a really good idea about what mathematics is, and if you've stopped taking classes with either differential equations or even a partial differential equations class in college, you probably don't know what mathematics is like yet. Then this would be a good place also to sort of get an idea about what mathematicians think mathematics is like. Not the way physicists and engineers think mathematics is like. A little difference there. So I think this is a good book. You might want to take a peek. I like it very much. I did have to reread it, so I had to pick books randomly out of my stash that I've read to get one that I've read to go through this because I looked at it 2 weeks ago and just knew that I had no idea what Gleason's theorem was. So I was So I went and looked at it again. So I'm sorry if those seemed a little short. They were a little short because I just sort of grabbed them off my shelf randomly. Thank you very much for listening, and I will find another one next week. And I'm going to try to get the latest episode of Physics Frontiers out next week as well, because classes start the week after that. So I might be slow in editing again, like I already am, I guess, right now, since I'm a couple weeks late on Physics Frontiers. All right, thanks for talking. Bye now.